Good morning, dear students. I hope you are doing well. Yesterday, we have started discussion on different types of top-down parser. And we completed one type of top-down parser that is called as a recursive descent parser. The second type of top-down parser that we are going to discuss today. Before that, let us discuss some of the disadvantages of recursive descent parser. Okay, because here one question arises that why, if recursive descent parser was there, then why, what was the need of top-down predictive or LL1 parser, the second kind of top-down parser? What was the need of that? So in the last part of the discussion, we just briefly identified that the top-down, the recursive descent parser is simple, but it cannot handle a larger grammar. Okay, that is one of the drawback. And it always, I mean, for every non-terminal, it uses a function, and through that function, it calls the non-terminal again and again. That is because of that only it is called as a recursive descent parser. And one more drawback that has been identified is backtracking. We have not discussed the backtracking part, and that is we are going to cover now. We are going to see how the backtracking happens using recursive descent parser. So this is one of the variant that we are going to discuss. One of the variant of recursive descent parser, and it is also called as recursive descent parser with backtracking. Okay. So, and one more drawback is sometimes the parser does not understand the grammar. So the modifications of the grammar also required sometimes. Additionally, the recursive descent parser, it does not accept left recursive grammar. Okay, no doubt, no top-down parser accept left recursive grammar. So there, the grammar need to be converted into non-left recursive grammar. Then only the grammar can fit into the recursive descent parser. Okay. So these are the few drawbacks that we observed yesterday, and we stopped discussion from recursive descent parser with backtracking. Backtracking is one of the major drawback of recursive descent parser. Okay, that we are going to realize now. So under lecture 9, we are going to discuss recursive descent parser with backtracking, and we will take one example to realize that. And if time permit, we'll discuss the second kind of top-down parser, that is the advanced version of top-down parser, that is called as predictive top-down parser or LL1 parser. Okay, so let us move on. I am Dr. Sudarshan Behra, Assistant Professor of CSE Department, and in the School of Computer Science and Artificial Intelligence in SR University. Okay, thank you. Let's move on. Okay, here is the topic. This one is called as a recursive descent parser with backtracking. Okay. Sometimes multiple productions exist, like A derive AB or A derive AC. Okay. A derive AB or A derive AC. The parser may choose a wrong production first, later return back to try another production. Okay. So this particular process is called as backtracking. Because what is the duty of parser? What is the role of parser? The role of parser is to generate the target string. The target string will be given and the grammar will be given. The role of parser is to generate the target string from the given grammar. By using what? By using the derivation, by using either leftmost derivation or rightmost derivation. Okay. So as a top-down parser, it always uses leftmost derivation. Okay. So by using leftmost derivation, the top-down parser try to generate the string. If the string generated successfully, then the string is accepted. I mean, the string is syntactically correct, okay, or grammatically valid. If not, in that case, we can say the string is, I mean, some error is associated with the string. Okay. So that is the role of top-down parser. Any top-down parser, you can say recursive or predictive parser. Okay. So here, if multiple, the thing is, if multiple productions are exist for a particular non-terminal, like A derive, capital A derive, small a b is one production. In the second production, you can see capital A derive, small a c. Okay. So here, if a desired string will be given or the target string will be given to the top down, I mean to the to the descent recursive descent parser, then the role of parser is to generate the string. So in order to generate the string, okay, in order to generate the string, sometimes the parser because the role of parser is to keep on attempting until it get the target string or the desired string. Okay. So sometimes in the production process, in the derivation process, okay, while deriving the string or while producing the string, the parser sometimes may choose a wrong production because A has two productions here. Okay, you imagine there could be 4, 5, or beyond that. I mean, n number of productions can be possible for A. So in that case, the parser takes more time to reach to the target production or the right production because here the target of the parser is to choose the right production so that the target string can be achieved or can be seen. Okay. If the parser does not choose the right production, so it may choose a wrong production and it may perform the matching function. If the match function does not occur, if the match does not occur, then the parser need to roll back the production. Okay. What production it already selected, that production it need to remove, then it go to another production. So this is the attempt of the recursive parser. And this process is called as, finally it may reach to the right production, no problem. It may reach to the right production or right production, or it may select the right production in one attempt, in two attempts, or in multiple attempts. So when the case of multiple attempts come, that means the parser may choose wrong productions initially. Okay. In the first attempt, second attempt, third attempt, fourth attempt, it may choose wrong productions. And finally, it may get the right production. Okay. To see the target string. So when multiple derivations are given or multiple productions are given, the parser may have a chance to select the wrong productions. So if the wrong production is selected, okay, then definitely it cannot see the target string. So again, the parser need to roll back. Okay. So see here the time, it is a time consuming method. Okay. So you select a wrong production, then when you identify, this one is a wrong production, then you need to roll back. You need to remove the production, then you fit another production. Then that production may be wrong one. Then you try for the third one, fourth one, and finally you may reach to the right one. But before you reach to the right production, you imagine how much time is consumed by this selecting and removing process. Okay, this is called as backtrack. Okay, first choose, apply, then see this is a wrong thing. I mean, realize this is a wrong production, then remove that production, go for the next one. and repeat the same thing. Okay. So this process is called as backtracking. Okay. So backtracking increases the parsing time and reduces the efficiency of the parser. Okay. So if the time increases, definitely the parser will not be efficient one. It will not perform the task on time. Okay. Now come to the definition of backtracking. Backtracking is the process in which the parser chooses a production, proceeds with parsing, detect the failure. Okay, that means when it identifies this is a wrong production, the parser get failed. Okay, so it detects the failure, it returns to the previous state by using a rollback technique. Remove the production. Okay, and it tries another alternative production. So this particular method is called as backtracking. Okay, which is a major drawback of recursive descent parsing. Okay. You see one grammar is given. Here S derived. This is an example. S derived small a followed by capital A. This is one production. Another production S derived small a followed by capital B, where A and B are non-terminals. Okay. And S is the first non-terminal. It is already given. Then A has a production that is A, capital A. Capital A derives small c and capital B derives small. Okay. So how many productions are given? 4 productions. Okay. In 4 production, 3 non-terminals are available. One is capital S, that is the start symbol of the grammar. Another one is capital A and another one is capital B. And this capital A and B has their separate productions. Okay, A producing small c, whereas B deriving small b, capital B deriving small b. Okay, so total 4 productions are given. And the input string is given AB. What is the input string? AB. So the grammar is now, the parser is now engaged to produce the string small a followed by small b, AB. Okay, it has 4 productions given. So now the question is which production the parser need to choose. Okay, it is visible to us. We are human beings. We can easily say that S derive AB because the first character should be A and the second character should be B. Okay, so S derive A. If you choose small a followed by capital A, later capital A need to be replaced by C. So what you are getting there, AC, that is not a valid string, not the target string. Rather, the target string is AB. So here we can easily say, sir, S derive AB. If I will take S derive small a followed by capital B, later I can replace capital B by its production called as small b. So I can easily reach to my target string, that is small a followed by small b. But the question is the parser is rightfully going to choose the same production? The right production at one attempt? No. Parser does not have brain. It cannot have eye to see, okay, to identify or to realize. Okay, so it is a completely program. So the program, you imagine this program is made using if-else statement. Okay, so how many if, how many else, and finally any one of the condition will be true. Okay, so here many productions are given. Ultimate 2 productions are given. The parser need to choose any one. Let us say that the parser choose the wrong production, that is S derive AB, small a followed by capital A. Then later on, capital A need to be replaced by C. And what will be the total string or the target string? What will be the output string it will get? It will get AC as an output string. But the string input string is given AB. So AC is not equal to A. So the parser failed. What production it is selected, that is gone wrong. Okay, now what the parser has to do? The parser has to completely remove that production small a followed by capital A. Okay, and it is going to select capital S, derive small a followed by capital. Later on, it will find out, it will replace the production of B with B. It will replace small b, okay? It will replace capital B by small b, and the total string can come out. The desired string or the target string can be seen, that is AB. Okay, so first the parser choose small a followed by capital A, which is gone wrong. Then the parser roll back and select small a followed by capital B. Okay, and later B is replaced with small b and the target string has been seen. So here 1 second or 1 nanosecond time is wasted by the parser. You imagine if multiple, there only 2 productions are given here. You imagine an example where there can be 10, 20 productions. In that case, how much time the parser will waste by choosing the wrong production one after another. Okay. So this process is time consuming, and the method is called as backtrack. Okay. So let us see this example further. Let us realize in terms of backtracking with recursive descent parser. Here you see step-by-step parsing with backtracking. Okay. Step 1, the action is start with capital S, because the derivation process start with the start symbol of the grammar, capital S. The production is applied. This is a wrong production, but you know and me know. But parser does not know. It is a program. It has a choice. Okay, it can see any alternative. It can take it. Okay, but it cannot see and choose the right production at one attempt. Okay, so here the production applied S derived small a followed by capital. The derivation is S derived A, small a followed by capital A. Step 2, it matches the input buffer, because in the input buffer, which one is loaded? The input string is loaded, that is AB. Okay, the person need to derive that string from the grammar, that is the row AB. So it will read first A from the input buffer, and it match with the sentential form, that is A, small a followed by capital A. A is matching, verifying, the parser move on. Okay, try to match. Then step 3, it expand the non-terminal, because in the second input symbol is B. Whenever it reads the second input symbol B, and it will see the second grammar symbol is capital A, so B is not equal to capital A. So capital A need to be expanded, because that is a non-terminal. So now capital A is expanded with its production. What is the production of A? That is small c. So A is expanded as small c. Okay, so what is the input loaded in the input buffer? A, which is already read. Now currently it is reading B, and simultaneously it is expanded A as C. So now B, small b, is not equal to C. Okay, okay, expected is C, but input has B. Input is B, which is not matching with C. Now here in this point, the parser fails. Okay, and it realized that this one is a wrong production. So now the person return back, roll back, return to S again, starting. S has 2 productions, small a, capital A, which already selected and taken as wrong. Next, it will look for the alternative production of S, that is S derived small a followed by capital. Okay, now try another production, S derived small a followed by capital. Now the derivation is S derived AB. Now step 6, it matches A with A as it is previously done. Now the second input, whenever it will read, because it will read as it is rolled back, it will the another pointer, the first pointer which is reading the input in the input buffer also, it will roll back to the original or to the first character of the input cell. Okay, so everything roll back, not only the grammar, the input buffer also reset to its original original position. The input pointer also reset to the original position, and it will rescan everything. It will start. A is matched with A, that is okay. Now, second input, whenever it reads B, it will identify that is a capital B, which is nothing but a non-term. But input buffer containing small b, but here in the grammar, in the production, it will identify a capital B. Now, it is try to expand capital because small b is not equals to capital. So when it apply expanding, it will apply B has a production. It will see whether B has a production or not. Yes, B has a production, that is capital B, derive small b. Okay. So finally, in the sentential form, or what sentence is generated? Small a followed by small b. Now it will read B matching, job is over. Okay. So now this is the right production because in the input buffer, it has, it reads AB as input character or input as input, and simultaneously it sees AB as the output of the grammar. So input is equal to output. Now the string is accepted. Okay. So this is the way the parser works with backtrack. Okay. Problem with backtracking. What problems has been observed when parser work with backtracking principle? Okay. The problem is, first of all, it is time consuming because it need to, if multiple productions are there, it need to, and whenever it choose a wrong production, it need to roll back. It is not only roll back in the grammar symbol or in the production process, not only the productions are getting rejected, and but also the input pointer, okay, which points to the input buffer, need to reset every time to the original position or to the initial position. So there are so two types of backtracking actually. One is select the wrong production and remove it, go to the start symbol of the grammar, or go to the intermediate node, okay, in the derivation process, okay, and simultaneously reset the input buffer, okay, reset the input buffer to the previous position. So that is called as, there are two types of backtracking. Okay, so in total it is a time consuming method. Parser may repeatedly retry productions. Okay, inefficient, extra computation is required, extra time, okay, so extra calculation, this is required, so that is why it is inefficient. Okay. Complex parsing, difficult for large grammar. This it does not support if the grammar is huge and complex. Okay. Slower compilation process because the parsing time it get increases. Okay. Because parsing time is more, so automatically the compilation process gets slow. I hope it is clear. Very good. Next, solution to the backtracking. What can be the possible solution so that this backtracking can be avoided, okay, or it can be eliminated? As backtracking has been observed with the recursive descent parser, some solutions are also acknowledged. Okay, so first of all, remove left recursion. Okay, if left recursive grammar is there, it is better to remove left recursion. Then apply left factoring. Left factoring is another technique, okay, through which if the multiple productions start with the same character, if a non-terminal has multiple productions and many of them are start with the same character, then the parser has a chance to choose the wrong production. So in that case, the that is called as left factoring. Okay, in that case, the left factoring need to be avoided. Okay, I mean the left factoring need to be applied so that the grammar can be cannot be a non-left factoring grammar. Okay. Next, uses predictive parsing or LL1 parsing. This because of all those shortcomings, okay, the second kind of parser, okay, second kind of parser that has been approached is called as top-down predictive parser or LL1 parser. No doubt there are the 2-3 other techniques to avoid backtracking, but the efficient approach or the finest approach that has been seen is a LL1 parser or top-down predictive parser. Okay. So from here, the top-down predictive parser came to the picture. Okay. Now read what is top-down predictive parser. The top-down predictive parser is also known as LL1 parsing or parsing technique, which is used in compiler design to analyze whether an input string belongs to a grammar. Okay. The same thing. It also perform leftmost derivation to derive the string, and it checks what string is there in the input buffer and what string is the output of the derivation. If both of them are matching, then the string is okay, grammatically correct. Otherwise, the string is grammatically ill or syntactically ill. Okay. So it is called predictive because, as per the names, a very good interesting thing. Why it is called as predictive? Because like previous parser, unlike previous parser, it does not choose the production randomly. Rather, before starting the parsing process, okay, what it does, it is select the right production. Okay, that means it predict which production will be useful at what time. Okay, so it does that by looking at the next input symbol, and it does not have any backtracking. Okay, so as it is, in advance, it is select what productions will be useful. Okay, and it store them in a table called as parsing table. That is why this parser is one step ahead than the previous parser. A very clever process. It is select or it predict the what type of productions will be useful at what time. Okay, based on the upcoming input symbol or next input symbol, it choose that. Okay, that is why this is known as predictive parser. Okay, ultimately it is also called as LL1 parser. Why? Because the LL1 in the LL1 first L stand for scanning the input from left to right. It is scan the input from left to right, as the previous parser also does the same thing. Every parser does the same thing. Okay, scanning input from the left to right. Then second L stand for adopt the leftmost derivation. So first L1, first L scanning the input from left to right. Second L indicates uh, leftmost derivation. I mean, it adopt leftmost derivation in order to carry out the parsing task. Okay, and one use one look ahead symbol to make the parsing decision. One means at a time it is scan one input symbol, and it looks only one input symbol as the next symbol in order to complete the task. Okay, by seeing that symbol, it predict what will be the right prediction. Okay, these are the some features of predictive parsing, top-down parsing method, because it start from the top and it reach to the bottom. It start from the start symbol of the grammar, and that is called as root, and it reach towards the leaf of the tree. Okay, that is why it is called as top-down parsing method, and it does not have backtracking. This is one of the most advantage of this parser. It uses a parsing table. As I said, a parsing table is a data structure which holds the useful productions, okay, which can be used in future, because it predict and store them in the data structure called as parsing table. This parsing table is also called as M table, capital M. Okay, it is efficient and simple to implement. It grammar must it does not accept non-left recursive grammar. Okay, sorry, so it does not accept left recursive grammar, and here the grammar must be left factor. Okay, so these are the features of top-down predictive parser or LL1 parser. Okay. LL1 parser has few components. Okay, it has four components as we discussed in previously for recursive descent parser. It has also same component, same type of component. One is input buffer, where in which holds the input. Okay, and the stack which holds the grammar symbol. Okay, and a parsing table is nothing but a data structure used to decide which production to apply. That means stores all the productions, and from the parsing table, whenever required, the parser picks a production and use it. Okay, so in that way, it does not have a chance to select a wrong production. Okay, and it has a program called as parsing program which controls the parsing operations. Okay, what is the working principle of this particular parser? This parser comprises top element of stack, and it reads two things at a time: input from the input buffer and what is the top of the element, what element is placed in the top of the stack. So both of them it reads simultaneously. One is input. It has 2 pointers. Remember, okay, 2 pointers. In fact, 3 pointers I can say. Okay, one pointer points to the parsing table. Sorry, one pointer points to the input buffer, which reads the current input symbol. Other pointer points to the top of the stack. Okay, and finally the parsing algorithm is there. After reading both the symbol, one from the input buffer, other from the stack, it matches whether the input symbol is matched with the stack symbol. If yes, then it is scan the next input and it is scan the next top of the stack. Okay. If it is remove the element from the top of the stack if matches found. Okay, if match occur, it will proceed to scan the second input symbol, and simultaneously it will pop up the stack, and it will points to the next symbol on the top of the stack. Okay, if again match found, then same thing will be carried. If match does not occur, I mean input symbol is not equals to stack top, then what it does? It is try to expand the top of the stack, because top of the stack, if it is not an input, it may be a non-terminal or it may be a terminal. If terminal and not matching, then total program is, there is one error in the input. Okay, if a non-terminal, then that non-terminal need to be expanded with its right production. Okay, so every time it matches input symbol with the every time the whenever it encounter a non-terminal on the top of the stack, and if the non-terminal is not matching with the input symbol, okay, then it expand and it always try to find out a terminal in the top of the stack so that the terminal can match with the input symbol and it can proceed forward. That is the type. Okay. Then finally it decide based on the number of input symbol available, or you may say whenever it reads all the input symbol and nothing will be there on the in the input buffer, and the stack reach to the bottom of the stack. That is a marker which indicates the bottom of the stack, normally called as dollar. If it reaches the bottom of the stack and nothing there on the top on the input in the input buffer to read, then that case the parser accept the input. Otherwise, it will reject. Okay, this is the working principle of this particular top-down predictive parser or LL1 parser. These are the steps in predictive parser. Okay, these are the steps. First one is remove left recursion. Okay, first one is remove left recursion. Second one is perform left factoring. How to remove left recursion? Yesterday we already discussed. This is the formula. If there is a production A derive A alpha or beta, because A it indicates, okay, leftmost A in the right hand side of the production is equal to the A which is present in the left hand side of the production. Okay, So both are identical. So it indicates it is a left recursion production. Okay, left recursive production. So in that case, it uses a secondary variable, that is to remove the left recursion. We have already seen this. Okay, that means the grammar can be rewritten as a derive beta a dash is a new non-terminal or variable, beta a dash, where a dash derive alpha a dash or epsilon. Okay, this is one method to remove left recursion. What is left factoring? I told you, if there are multiple productions for a non-terminal and most of the productions start with same symbol, then in that case that is called as left factoring. This left factoring need to be eliminated. Okay, so how can, here you can see a derive a, small a b, and another production capital A derive small a c. That means capital A is a single non-terminal. It has two productions. Capital A derive small a followed by small b. This is one production. Second one, capital A derive small a followed by small c. Okay, in both the production you see a small a is appearing first. So this kind of thing is called as left factoring. This need to be eliminated. Okay, so you apply left factoring. You apply some formula to eliminate left. So what is that? A derive, capital A derive. This grammar can be rewritten by using a new variable, that is a dash. So A derive a dash, small a followed by capital A dash. Whereas capital A dash can be written as B or C. Okay. So here capital A has only one production, that is small a followed by capital A dash. This is fine production. Then capital A dash has two productions, but none of them are identical. I mean, none of them are starting with the same input symbol. One is B and another one is C. Okay. Now here left factoring is also eliminated. Okay. These are the steps before you apply any grammar to the predictive parser. So ensure that left recursion should not be there, and left factoring also eliminated. Then find out the first and follow. What is first? These are the two functions by using, because first and follow is required to construct the parsing table. Okay, for that it uses two functions, first and follow. What is first? First contain all the contains a terminal that appears that appears in the first position of a sentential form. Okay, or that appears first in the derivation. Okay, similarly follow of a non-terminal can follow of a non-terminal is a terminal symbol or is a symbol. Okay, and it must be terminal. Okay, follow contains terminals that appear immediately after a non-terminal. If non-terminal is A and follow is, and after that small c is there, then small c will be taken as the follow of capital A. Okay, anything that immediately appears after that symbol or the non-terminal can be considered as a follow if that is a terminal symbol. If not, then it can be further expanded. Okay. So construct predictive parsing table. Okay, for every product, this is the rule. For every production A derive alpha. Okay, put production M. M means the parsing table I said already. Okay, M of capital A comma A for all A belongs to first of alpha. If small a is an element of first of alpha, okay, then M of that coordinates capital A comma A, okay, you must put the production A derive alpha. Okay. If epsilon is there in the first of alpha, then place M of, in the place of M of A comma B, okay, put plus production in M of, okay, plus that production A derive epsilon in M of A comma B, where B is a follow of capital A. Okay, B is a follow of capital A. I know it is difficult for you because it is little difficult to convince without example. So our next target is to, these are the 4 steps that we came to know. Okay, the major steps are, okay, let us assume the grammar does not have left recursion and not left factoring. The grammar is fine. Then you have only remaining 2 steps. Okay, first calculate first and follow, then construct the parsing table as per the rules given. Okay, this thing we are going to see in the next, in the next slide. Okay, this is the parsing algorithm that we will discuss in the next class. Okay, I wish you all the best and keep liking, do subscribe, and hope you all are doing well. Have a nice day. Okay, rest we will discuss in the in the next class. Thank you. Have a nice day. Bye.